Young's double slit experiment, YDSC. So this is the experiment done by Thomas Young in 1802. Here he used two slits which are separated by a small distance d here, and a screen is placed at a distance capital D from these slits. Now this is the midpoint of the screen. When the waves from S1 and S2 meeting at this point, you can see the distance traveled by this wave and distance traveled by this wave to reach this point will be same. So what is the path difference between these two waves while reaching the center of the screen? So at center of screen, the path difference between the two waves is 0 as they travel equal distance. Why? Because here S1P is S1O is equal to S2O. So the path difference is 0. So at the center of the screen always we will get a bright fringe. So that fringe we call it as central bright fringe, CBF. So at the center of screen always a bright fringe is formed. Reason is the path difference is 0 as well as the phase difference is also 0 between these two. Now if you take another point on the screen which we are taking as P here, so let me erase this one here. Now if the wave strikes the point P here and here, now what is the path difference between these two? Now at point P, so we can write here the path difference is given by distance traveled by the second wave minus distance traveled by the first wave. Why? Because from the diagram itself it is clear that S2P greater than S1P. So how to find the path difference here? To find out the path difference, see S1P is this much. If you draw a perpendicular here, and this will become S1P and this is also S1P. So this is the extra path traveled by the second wave here. So I am going to denote this as a delta x and this angle is theta. Now if you join this point like this and this is also theta, this angle is also theta. Now if theta is very small, we can write if theta is very small, we can write sin theta is equal to tan theta which is equal to theta. Now first of all let me find out the distance of this point P from the center of the screen. So as it is along y axis, I am going to keep this as y only here. So this is y. So from the trigonometry I can write sin theta is equal to here opposite side by hypotenuse. If theta is very small, this sin theta can also be written as tan theta, which you can write it as y by d. This is equation 1. Similarly, if you take this small triangle S1, let us say this is a Q here. So from this triangle, what is the sin theta? Opposite side by hypotenuse. So from this triangle, from triangle S1, S2, Q, we can write sin theta as the opposite side, that is delta x by hypotenuse d. This is equation 2. You can see this is sin theta which is also equal to tan theta. Here also this is sin theta. These two are equal. So from this I can write delta x by small d is equal to y by capital D. So that the path difference in this case is y small d by capital D. Now if at point P, if a bright fringe is formed, compulsory the path difference must be equal to n lambda. If P is a bright fringe, then we can write delta x must be equal to n lambda because this is a bright fringe. So in place of delta x you write n lambda. So now I am going to take this formula and this is equal to yd by capital D. So now from this we can write y is equal to capital D n lambda by small d. This is a distance of that bright fringe here. Distance of the bright fringe along y-axis or from center of the screen is given by capital D is the distance between the slit and screen, and n is the number of the order of the fringe, lambda is the wavelength used, and d is the distance between two slits. So this is a position of bright fringe from center of screen. Now for first bright fringe, n will become 1 and this will become y1b is equal capital D lambda by small d. For second bright fringe, n is equal to 2, you can write y2b is equal d or 2 capital D lambda by small d. The distance between two successive bright fringes or two successive dark fringes is called fringe width. So what is the fringe width now? The fringe width is given by beta is the distance between two successive bright fringes. This is the distance of the second bright fringe. This is the distance of the first bright fringe from the central maximum or central bright fringe. So this is equal to y2b minus y1b. So now if you subtract these two, you will get 2 capital D lambda by small d minus capital lambda by small d. So fringe width is given by capital D lambda by small d. This is the fringe width here. Is a dark fringe, then we can write the path difference must be equal to 2n minus 1 into lambda by 2. This is the condition for the dark fringe. And in this case, the path difference is given by yd by capital D. So if you compare these two, you can write yd by capital D is equal to 2n minus 1 into lambda by 2. So y is equal to capital D by small d 2n minus 1 into lambda by 2. So this is the distance of that point P from the center bright fringe if it is a dark fringe. So for first dark, we can write y1d. The meaning is distance of y due to that first dark fringe from the center is given by. So substitute n is equal to 1 here. 2 1s are 2 minus 1 1. So this will become capital D lambda by 2d. For second dark fringe, y2d is equal, so you can substitute here, 2 are 4 minus 1 3, so 3 capital D lambda by 2d here. So what is the fringe width in this case? Fringe width is the distance between two successive bright fringes or two successive dark fringes. So now the fringe width is given by y2d minus y1d, 3 minus 1 2, 2 capital D lambda by 2d, this is cancelled, capital D lambda by small d. So this is the fringe width in this case. If the whole apparatus of Ydse is immersed in water, immersed in a liquid first of refractive index n, then what happens? The fringe width in air is given by capital D lambda by small d equation 1. But when this is immersed in water or the liquid, here I am denoting this as liquid, then what happens? So this capital D and small d will not change, but the wavelength of light in air is lambda, but wavelength of light in the liquid is decreased by n times. This will become lambda by n. So from this what we can write? The fringe width when the Yd apparatus is immersed in water is going by capital D lambda by small d by n, which is equal to beta air by n. That means whenever this Ydse apparatus is immersed in water, the fringe width decreases by n times. Suppose if the liquid is water, so in water what happens? The fringe width decreases by beta dash is equal to beta by n water, that is beta by, for refractive index of water, we know that n is equal to 4 by 3, so I am writing 4 by 3, so this will become 0.75 times the fringe width in air. This is the fringe width in air. So what is the fractional change in fringe width when it immersed in a liquid? So here I am writing fractional change means change in fringe width by original fringe width. So change in fringe width is the bigger fringe width, that is air, minus beta in liquid by beta in air. So what is beta in air? That is capital D lambda by small d. So I am going to write this as beta only, but in liquid it decreases by n times by beta. So if you take beta common, 1 minus 1 by n by beta, you can cancel this one. So percentage decrease in the fringe width when the apparatus is immersed in a liquid is given by 1 minus 1 by n. So what is this? This is a fractional change in fringe width. What is percentage change in fringe width? That is delta beta by beta into 100 is equal. This can be written as 1 minus 1 by n into 100 or n minus 1 by n into 100%. IDSC, the distance between the two slits and screen is 2 meter. Distance between the two slits is 1 millimeter. Lambda is 5000 angstroms. Find the fringe width. Distance of the fourth bright fringe from the center. Distance of the fourth dark fringe from the center. So first of all, let me find out beta here. This is going to be capital D lambda by small d. What is capital D here given as 2 meter? Lambda can be written as 5 into 10 power minus 7. Why? Because this is 5000 into 10 power minus 10 meter, which is equal to 5 into 10 power minus 7 by the small d, the distance between two slits, which is given by this is 1 millimeter. So this is 2 5s are 10 into 10 power minus 4 or 10 power minus 3 meters. So this is 1 millimeter once again. So fringe width formed on the screen will be 1 millimeter. Now what is the distance of the fourth bright fringe? So we know that the path difference delta x is equal to y n d by d, which is equal to the fourth bright fringe. So this will become 4 lambda. Why? Because n lambda will become 4 lambda. So this y will become 4 lambda d by small d. This is a fourth bright fringe. So that's why I'm writing n is equal to 4 here. So this is n lambda actually, but n is equal to 4 in this problem. So this is nothing but 4 into capital D lambda by small d. This is nothing but the fringe width which we got here, 10 power minus 3. So distance of the fourth bright fringe from the central bright fringe is given by 4 into 10 power minus 3 meters. Similarly, what is the distance of the fourth dark fringe? So as it is, we can write the fourth dark fringe is given by y fourth dark fringe is given by, our formula is 2n minus 1 capital D lambda by 2 small d. This is actually capital by small d, 2n minus 1 into lambda by 2. So this is n is 4 here, 2 4s are 8 minus 1, 7 capital D lambda by small d by 2. This is nothing but 3.5, and this is the fringe width which we got previously got as 10 power minus 3. So distance of the fourth dark fringe from the central maximum is given by 3.5 into 10 power minus 3 meters. Here another problem in YDSC, capital D is 2 meter, small d is 0.1 millimeter, wavelength user is 5000. Find the distance between sixth bright and fourth dark fringes. So I need this value y is equal to y of 6b, that is distance of the sixth bright fringe from the central maximum, minus y of fourth dark fringe here. So this can be written as 6 into capital D lambda by small d minus, this is fourth one, or otherwise I can write this as a n into capital D lambda small d. This is 2n minus 1 into capital D lambda by small d by 2 here. Here for bright fringe n is equal to 6, so directly I am writing capital D lambda by small d. For dark fringe n is equal to 4, 2 4s are 8 minus 1, 7 by 2 into capital D lambda by small d. So you can take capital D lambda by small d common, 6 minus 3.5, which is equal to 2.5 capital D lambda by small d. So you can write 2.5 into, you can substitute this capital D lambda small d now, capital D 2 lambda 5 into 10 power minus 7, small d 0.1 10 power minus 3 are directly 10 power minus 4. So this is 2.5 into 2 will be 5, 5 5s are 25 here, this is 10 power minus 3. So this is the distance between the 6th bright fringe and 4th dark fringe in YDSC. In YDSC, the wavelength of light usually is 5000 angstroms and the distance between the two slits is 1 millimeter. Find angular fringe width. What is this angular fringe width? Let us say this is S1, this is S2, this distance is D. A fringe is formed here whose fringe width is beta and this distance is D. The angle made by this fringe at one of the slit is called angular fringe width. So this angular fringe width is given by beta by capital D. So sin theta can be written as tan theta and theta is very small. You can write sin theta is beta by something or tan theta is beta by D. So this can be written as beta by D here. Now what is beta? Capital D lambda by small d, that is the fringe width there, by capital D, these two get cancelled. The angular fringe width is given by wavelength of the light used by distance between the two slits. So what is this lambda? Lambda is equal to 5 into 10 power minus 7 by, this is 10 power minus 3. So this will come 5 into 10 power minus 4. This is in radians because theta is measured in radians but not in degrees. In YDSC, find lambda 1 by lambda 2 if 6th bright fringe formed due to the wavelength lambda 1 coincides with the 4th dark fringe of light used of wavelength lambda 2. So here 6th bright fringe coincides with 4th dark fringe. So for this to happen, what is the condition for bright fringe? The path difference must be equal to n lambda. So here the path difference for this one is equal to n lambda or delta x is also equal to 6 lambda 1 because the wavelength is lambda 1. Similarly for the 4th dark fringe, delta x must be equal to 2n minus 1 into lambda by 2. So now here n is equal to 4. So from this we can write delta x is equal to 2 4s are 8 minus 1 into lambda 2 by 2. So now here we got delta x is equal to 6 lambda 1. Here delta x is equal to 2 4s are 8 minus 1, 7 lambda 2 by 2. Now when these two are equal we can write 6 lambda 1 is equal 7 lambda 2 by 2. So we can write lambda 1 by lambda 2 is equal to, this is 7 by 12. This is the ratio of the wavelengths of light used in this problem to have or to coincide with the 6th bright fringe with the 4th dark fringe. In YDSC, the setup is moved from air to water. Find the percentage decrease in fringe width. In air, beta in air is equal to beta. Beta when immersed in water is given by beta by n water. So what is the percentage decrease? Here this fringe width decreases by n times here, where n water equal to 4 by 3. So percentage decrease in the fringe width is given by delta beta by beta into 100, which is given by, what is delta beta? That is change in fringe width. That is beta minus beta water by beta air into 100 here. So this is beta air, this is beta air, this is 1 minus beta water by beta air into 100. So this is 1 minus beta water is nothing but beta air by 4 by 3. So beta air by 4 by 3 by beta air into 100. Beta air get cancelled. This will become 1 minus 1 by 4 by 3 will become 4 by 3 into 100. This is 4 minus 1. 1 by 4 into 100, which is equal to 25%. So fringe width decreased by 25% in this problem. In another problem here in YDSC, the distance between two slits is 1 millimeter, wavelength is 5000 angstroms. Find the maximum order of the bright fringes formed on the screen there. So for this to happen, as they are asking the bright fringes, the path difference must be equal to delta x is equal to n lambda. So for this to happen, maximum order means n should be maximum. But what is delta x here? Here we found that this delta x is given by d sine theta. So by sine theta is equal to delta x by d, or delta x is equal to d sine theta. Now this must be equal to d sine theta, which is equal to n lambda. So n is equal to d sine theta by lambda. Now for this n to be maximum, because they are asking the maximum order, n value should be maximum. So n max is equal to d by lambda into, this value must be maximum only if theta is equal to 90. So this must be equal to sine pi by 2 radians. So n max is given by d by lambda into 1. But what is small d here? Here it is given as 1 millimeter, 10 power minus 3, and the wavelength is 5 into 10 power minus 7. 5 into 10 power minus 7. This is 1 by 5 into 10 power 4 here. So this is equal to 10,000 by 5, which is equal to 2,000. So the maximum order on that side, that means from the central bright fringe you will get 200 bright fringes. Similarly, and below this central bright fringe also we will get 200 bright fringes. So altogether 2000 plus 2000 together will be 4000 plus one central bright fringe. So total number of fringes formed on the screen are 2000 above central bright fringe, 2000 below central bright fringe, and one central bright fringe. So answer is 2000 plus central fringe 1 plus 2000, which is equal to 4001 in this problem. IDSC, either a bright fringe or a dark fringe is formed in front of any one of the slit. In front of any slit, then what is the condition for this one? So here it is given that this is S1, this is S2, exactly opposite this one. Let us say one bright fringe is formed. So what is the condition for this one? This distance is d, this distance is small d here, and this will become root over capital D square plus small d square. Now what is the path difference between these two waves, this and this? The path difference is given by S2, let us say this point is P here, this can be written as S2P minus S1P. What is S2P here? Root over capital D square plus small d square. S1P is nothing but the distance between the slit and screen. Here it is given as capital D in this problem also. Now this can be written as root over d square into 1 plus d square by d square minus d. So you can write this as d square into 1 is d square. D square and this one d square, if you cancel, this will be half. So now when it comes outside, this will become d root over 1 plus d square by d square minus capital D. So this d will become 1 plus d square by d square whole power 1 by 2 minus d. So from this we can write, if you take a d common here, this can be written as 1 plus half into d square by d square minus capital D here. Now you multiply this one, d into 1 will become, this is a binomial explanation. If 1 plus x whole power n can be written as 1 plus nx, if x is much lesser than 1 here. If this value is very less when compared to 1, you can write this as 1 plus x whole power n is 1 plus nx. So this is d into 1 will be d here plus d into small d square by 2 capital D square minus d here. So now you can cancel this d and d here, these two will get cancelled. This will become d square by 2d. This is the path difference between the two waves that are arriving at this point P. Now if this path difference is equal to n lambda, P will be a bright fringe. So now what is this path difference? This is equal to d square by 2d is equal to n lambda. Then this will be a bright fringe here. So for this to happen, For this to happen, this d square must be equal to 2d n lambda, or d must be equal to root over 2 capital D n lambda for the bright fringe to be formed here. This is the bright fringe. If it is a dark fringe, then you can write this must be equal to 2n minus 1 into lambda by 2. So, for dark fringe, this must be equal to 2n minus 1 into lambda by 2. So, from this you can write this is into 2d, this 2 to get cancelled, and d will be equal to root over 2n minus 1 into lambda into d. This is the condition for dark fringe. Ydse, effect of thin transparent sheet on a fringe pattern. Here, let us say we have a fringe here at point P. So, what is the time taken by this light to travel from S1 to P? So, time taken by light to travel S1P in air, to travel S1P in air, S1P distance in air. So, we need time. So, speed is equal to distance by time, and the time is equal to distance by speed here. So, the time here I will take it as t1. So, what is the distance traveled here? This is nothing but S1P. And what is the speed here as it is in air? So, let me take it as a speed of light which is equal to 3 in 10 power 8. This is equation 1. Now, in the path of this light beam, let us say if I keep a thin transparent film like a glass slab here. So, due to this, what happens? As the light is trying to pass through this one, it will bend here, and refraction will take place through this film, and this will be striking the screen at a dash point P dash now. So, what is the time taken by the light to travel from S1 to P through the transparent sheet? So, time through transparent sheet. So, in this case, first light is traveling from here to here in air, from here to here also in air. Let us say the thickness of this plate or transparent sheet is T. So, what is the distance traveled by the light in air only? From S1 to P minus T. So, this is given by T2 is equal, total distance is S1P minus thickness of the glass plate by this speed of light C plus, and the light is traveling through the transparent film through a thickness T. So, here this will be T by speed of light in that transparent glass plate will be not equal to 3 in 10 power 8, it will be V only. But we know that if refractive index of this transparent plate is N is equal to C by V, or V is equal to C by N. So, this can be written as T2 is equal S1P minus T by C plus T by V is equal to C by N. So, from this denominator is same here. So, you can write denominator as C. This will be S1P plus NT minus T. So, now the time taken is given by S1P is the total distance plus here NT minus 1T. If you take T common, N minus 1 by C. So, what is the actual path traveled in the first case? S1P only. What is the total path traveled in the second case? S1P plus this is the extra path traveled. So, this is the path difference between the previous one and this one. So, in this case, whenever a thin transparent sheet of refractive index N and thickness T are placed in one of the light beam, then the path difference is given by, this is the path difference, extra path traveled here is N minus 1 into 2T, where N is the refractive index of the transparent sheet and T is the thickness of the transparent sheet. So, whenever there is a path difference, instead of producing a fringe at P, this will produce a fringe at P dash here. So, this will be the path difference which is equal to y small d by capital D is equal to n minus 1 into t. So this y can be written as capital D by small d n minus 1 into t. Very important expression for competitive exam. This path difference as well as the position of this point from the center of bright fringe is given by capital D by small d into this path difference n minus 1 into t. See, capital D is 2 meter, small d 1 millimeter, lambda 5000, and a thin sheet of refractive index 1.5 thickness 100 micrometer is placed in one of the beam. Then find the path difference, shift in the fringe pattern, and number of fringes crossing a given point. First of all, path difference. The path difference is given by delta x is equal to n minus 1 into t. N is equal to 1.5 minus 1 into the thickness of this one is 100 micro. So this is 0.5 into 10 power minus 4. So this is 5. This is 0.5. That is 5 by 10. So 10 when goes up, 5 into 10 power minus 5 meters. So this is the path difference between these two. Now the second part is shift in the fringe pattern. Actually the fringe pattern will be formed here, but it will shift by a small distance. This is given by this delta y here. So this is delta y. This delta y is the shift produced in this one, which is given by capital D by small d, n minus 1 into t. Capital D is 2 meter, small d is 10 power minus 3, and n minus 1 into t is the path difference here, which is equal to 5 into 10 power minus 5. So this will be 5 2s are 10 into 10 power minus 4 become 10 power minus 4 by 10 power minus 3. So this is 10 power minus 1 meter or 0.1 meter. So this is the shift produced here on the screen. The third one is number of fringes crossing a given point. So if you take any given point here, how many fringes are passing through this one? Now we can write the number of fringes crossing a given point is given by this is delta y by beta. That is in this one how many fringes are passing here. So if you know the fringe width of each fringe and if you know this delta y, you can find the number of fringes crossing in that given through that point. So here this delta y is given by capital D by small d n minus 1 into t by beta is capital D lambda by small d. Capital D by small d, capital D by small d cancel. So the number of fringes that are passing through this point will be n minus 1 into t by lambda. Once again n minus 1 into t is this much, which is the known value here, 5 into 10 power minus 5 by wavelength is 5 into 10 power minus 7, 5 into 10 power minus 7, minus 7 goes up 10 power plus 7. So this will become 10 power 7 minus 5 2. So this is answer is 100 here.